All I care about is the whiteboard. So it's running now.
If you want it to tell you, oh, you're not in the frame. It's good.
Yeah, or when this goes to 29 minutes, it has to be restarted.
I'll tell you when you're.
It's probably having a little bit of a hard time focusing. Did I plug it in? No, I plugged it in.
Oh, you're recording right now.
Yeah. All right, guys. I've already started. Is it focusing on me now?
Yeah. Yeah, you're like right in the center.
All right. So I'm gonna break this up into this problem, this huge giant problem set. I'm gonna break it up. Hello. All right. I'm gonna break it up into three big chunks. You already did the first chunk, and now I'm gonna do statics and talk about this a little bit more. Okay. Now, if you have, remember we started out with the force. Well, that's terrible. Let's do this here. V dot equals the sum of the forces in whatever direction that you're concerned about. If this is direction I, that could be X, Y, or Z. This is, no, I don't like that either. Let's just talk about the direction of X for now. Now this is the sum of the forces in the X direction. And I need space for a subscript. Because we're summing up over all the forces. Let's just put it as a, like that. What I mean is that all this is along one direction. Because I'm not going to talk about, I'm not going to make this vectors, and I'm going to show you. I'm breaking this up. Our original equation was like this. This is a vector, and this is a vector, right? Well, you can treat these separately since these are linear functions. That means there's no square here, right? There's no square root or anything like that. If you double this, you double that. That's our linear relationship. Well, you can separate, these are the vectors, but you can break these up into components just like you can regular vectors. So we can talk about the sum of the forces. Oh my goodness. Here we go. She's back. All right. So this could be broken up into two. Instead of using vectors, we're going to break it up into components. Is that fair?
See?
Yeah. So then let's talk about this. P dot X. Sum of the forces in the X direction. Notice there's no vector symbol anymore, and this has a subscript to X. I need to leave room for the I here because that's just saying you're summing over all the forces. And this could be rewritten as, if the mass is constant, mass times the first time derivative of velocity for you calculus people. There's a lot of calculus people in here. That's why I'm throwing in a little extra. Give me a little extra. But for those who haven't had calculus, no worries. Just mass times acceleration. Yeah? And this is in the X direction only. These are not vectors.
What's on top of that summation?
In X, in all X. Just in X. I couldn't figure a good place to put it. I put it here, but I didn't like that either. So then we can do the same thing for the Y. In all Y. M V dot in the Y direction. M A in the Y direction. So I've just broken it out. And this is when you're going to use this, and I'll apply examples right away. So then maybe this will make a little more sense after I do some examples. If this isn't making sense to you yet. I'm just saying this could be split up. This is our original equation that we worked with. We could split it up like this in the x and y. That's all I'm saying. And I'm being really general about it and really nerdy about it. Okay. Can I erase this now? Or are you guys still going? Yeah? Okay. Now, so as I promised, just move quickly into make this a little less here. This is supposed to be 60 degrees. 30 degrees. Now if I have a mass hanging from some cables here, and I want you to find tension 1 and tension 2. This is just some mass M. We can give it a value. Mass equals 10 kilograms. Okay? And we're gonna just for the sake of simplicity, we're gonna round gravity off to 10 meters per second squared. And you can do that even on the test. You're not allowed to use the calculator on the AP Physics test. So in that case, you might make a statement, hey, I'm going to use 10 for acceleration of gravity, and that's okay. That's been okay in the past. They've changed stuff, so I'd have to check into that, but I don't think there's a problem with that. So we'll do that. Now what we do to solve this problem is what's called a free body diagram, and this is where you've got to be really careful. Make sure you, and I'm going to write this down, are only labeling forces that are acting on the system. In other words, this tension of this rope is causing another force, another kind of reaction force to go back here on the wall. But this thing is attached to walls. You don't care about that. You don't care about any of that other stuff. It's only the forces that are affecting, actually it's pulling this way. Because the tension force is going that way. So there's a reaction force here, right? The little eyelet that's if this is a cable and there's a little eyelet in a brick wall, that eyelet's trying to get pulled out of the wall, right?
Yeah.
Do we care about that force? No. It's only the force that's affecting the object in question, the system whatever we define as a system. And no need to pick something that we're not concerned about being a part of the system. You just make your thing way more complicated than it needs to be. Make sure you're only labeling forces that are acting on the system. This is called a free body diagram. So draw vectors, this is mg, this is tension 1, tension 2. You want to draw your vectors. And can you see, is it possible for these three vectors to cancel out here? It is. Yeah, because this has even though the angles are different, they can kind of compensate for that automatically, which is kind of cool. Because now you can do a little thought experiment. Oscar, you can ask yourself, is it possible having cables configured like this for these force vectors to cancel out? And the answer is obvious yes, because can you wire something like this and have it not move? Yeah. So it has to cancel out, right? If not, Newton was wrong. His assumptions are wrong. And I don't think you're going to find that he's wrong in something as simple as this. Maybe, some complicated thing where something's moving near the speed of light, but not in a simple setup like this. So I made this point, so let's crank this out. I'll leave my diagram here. I'm recording this little area, so I'm going to use this board to do my math calculations. Just remind me to put it in and out when I need to. Okay, and the way we do this is we call it sum of the forces and the x. And this is going to equal 0. Because the thing is, there's something crucial here, guys. There's a misstep that many people make. Does this mean it's not accelerating or it's not moving? Or both?
It's not accelerating.
It's not accelerating. It'd still be moving, but not accelerating. Because there's no velocity function, right, in that original set of equations that I gave you? There's a velocity dot, but velocity dot's not the same as velocity. So that's important. So if that says 0, don't mistake. Oh, this boat that's getting towed is moving, so I can't use this, the fact that this is 0. No, if it's not accelerating, this is okay. All right, so the sum of the forces in the x direction. There's tension 1. And what, define the x component of this vector, what trig function do you use? Cosine. And what's the cosine of 30 degrees? It's on your unit circle. Yes. Square root of 3/2. Okay? Oh, is this in the negative? Let's define our coordinates too. We got to do that. This is x positive, this is y positive. So is that negative or positive? Negative, correct. Because we're not using vectors here, remember. We have to watch the signs ourselves. With vectors, the signs take care of themselves. When we do it like this, you have to tell it what direction it's pointing. Okay, the other one, and this comes from T1 cosine theta 1, which I should have probably, this is theta 1. We'll call this one theta 2. So that's T1 cosine theta 1. Make sure that's in the camera. You guys didn't remind me. How we doing? Okay. So T1 cosine theta minus T1, that's the cosine of 30 degrees, plus, because it's in the positive direction instead of the negative direction, this is cosine, I'll just write this up here just to show you where I got this, remind you where I got this from, cosine of theta 2. What's the cosine of 60? The cosine of 60 is 1/2, yeah. And that's all equal to 0. See how that works? Who's playing on the computer? Really? While I'm lecturing? That's pretty bad, dude. Who's this for? Lauren? They want you. At 8:27. Oh, you don't need to go anywhere. This is just a delivery, right? Okay. Alrighty. Don't do that again. Alright, so now the next one. The sum of the forces, 0 equals the sum of the forces in the y. Okay. So what? There's 3 forces in the y now, right? You guys see that? We got y components of T1, y components of T2, and then mg. Let's do mg first since it's pure. What direction is it going? Negative or positive? Okay. Now these are going to be reversed, right, for the sine function? Because now we need the sine. You guys see that? Okay. So then this is going to be, they're both going to be positive though, because the y component of these two vectors are both positive. You guys see that?
Yeah.
Does everybody see that? Stop me if you don't see that.
Why does that have to be sine?
Because you're trying to find the opposite. If these are the angles, you're trying to find the y component of these tension vectors. Yeah?
Which is the one.
All right. Good. I'm glad you're asking questions. That's always a good sign. T2.
Good sign.
That's cute. There's a little pun right there. You see that? And that's going to be 3-2. That doesn't look like a good 3. And that's all equal to 0 as well. So now you have 2 equations and how many unknowns?
T1 is still negative, or is it like changed to positive?
They're both positive because they're both pointing up. The Y components are both pointing up for these tensions. Think about that. Convince yourself of that.
Okay.
Is everybody convinced that they're both positive? They're like goalposts. One might be higher than the other though. Okay. So now let's solve. So what's the easiest way to solve? We can just let's solve for T2 so we can eliminate T2. T2, bring all this other stuff to the other side, mg minus T1 1/2. Then we divide both sides by 3/2. That puts square root of 3 here, and then we can just multiply the quantity by 2.
Is this for the Y component or the X?
Can you guys see this? I mean, can the camera
yeah,
see
yeah.
this? Now, I'm sure it can now, right?
Yeah.
Okay.
Is that okay?
Wait.
Yeah.
How?
I just solved for T2, but I still have this T1, so I'm going to have to... Did I make a mistake?
Why did
I'm
the-
solving for T2 so I can plug it in here, collect terms.
How did the sign switch? It was
Huh?
negative.
Because I brought it over the other side. This guy's what I was solving for, right? This T2.
Wait, so you left that one there and you moved the other two to the
I
other
moved
side?
this to the other side.
Oh, okay, okay.
The sign flipped.
No.
I moved this to the other side. The sign flipped as
Okay.
well.
Yeah, I understand.
I thought you did this on
Now I can simplify a little bit. 2mg minus T1, and that kills this 1/2 thing here, but I still got this over the square root of 3. Now I can take this bad boy and plug it into here. But before we do that, let's solve for T1. See if we have room over here. This should be in the thing, right? This is the video?
Yeah.
Okay. So,
Let's see.
salud. T1, 3/2 equals T2, 1/2. Well, we can see right there, we can get rid of this 2. And that just leaves T1 equals root of 3 over T2. Well, that's kind of nice. Because that's going to get rid of that square root when I substitute in. So let's sub in T2. Yeah? Yes? All right. 2mg minus T1 over this guy. Let's see, we have this here. We can divide both sides, and that just ends up getting rid of the root. Because it's like squaring that guy right there. So T1. Now we have to collect like terms.
Is T1 and T2 the same in like the X and Y?
I'm sorry, what?
Is T1 and T2 the same in like the X direction and Y direction?
Yes. They're identical. And because this is the magnitude, right? This is the hypotenuse in that little triangle,
Yeah.
T1. So it is the same for both. By adding this, I turn it into an X component. Does that make sense? Okay. All right. So now let's collect like terms. So bringing this over the other side, I got T1 plus T1 over 3 equals 2/3 mg.
What was the mass of the object again?
It was 10 kilograms. I'm not going to put numbers until the very end. Okay, so then you can factor out this T1, and that leaves this. T1, 1 plus 1/3. That's just 4/3, right? Yeah? 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 4/3. That's kind of nice. This implies that T1, now I can cancel all these, I don't want to do that yet because I'm making this thing over here, so let's do that. T 2/3 equals, sorry, that's an mg. 2/3 mg equals T1 over 4/3. That cancels that. That cancels that. So then T1's going to be, yeah, we can simplify. We can get rid of this. And then finally we get T1. And we can write the tension 1 is equal to half of mg. So that'd be 50 newtons of force. Because mg, 10 kilograms times the acceleration of gravity is 10 to the 100. Or 50 newtons. Yeah.
What's your question? Why did you say T1 equal to T2?
Because this first equation, I could do that. You see that? Just bring this over to this side, and then that's what I got. Now we can use this again, right? We could still leave this off. Because that's just a simplification.
What did you do after, what was the last thing you did there? Because I got lost at like, after you, like found T2, I guess, kind of. Like you made T2 equals T1 times the square root of 3, and then I did 2, you did, yeah, like that, and then what did you do?
I substituted this guy in that I solved for T2. This got subbed into here. And then I collected terms. And factored out the T1. Okay? All right, so this is pretty easy now. You just sub in T1 and you get the answer right off. It's yeah? Is that right? Check my work. Yeah, but this is beautiful.
All right.
And then this is going to be some decimal value. Now, you should be able to go back and put these in, and they should satisfy in order to double check, right? Okay, so let's see if it satisfies this equation. T1 minus T1. Well, let's plug in what T1 is. T1 is mg over half, right?
Yeah.
Times 3/2. And we'll just set up these equal because I can move this negative one on this side and it just becomes. Okay? Now this one is 1/2. Yeah? And then, look at that.
Wouldn't it be negative 1/2 since you're moving
No,
to the other
because you
side?
pulled it to the other side. I pulled the negative one to the other side.
God.
So you can multiply.
Or I could pull this to this side, it becomes negative. They're both negative, I can multiply them both by -1.
So if you multiply everything by 2, then
Well, you can see there's the 1/2, there's the 1/2, there's the 3/2, there's the 3/2. You see that? Yes, ma'am.
Is that sigma f of x or sigma f of y? Well, that you're solving for right now. Or is it just...
I just plugged it back into the original equation to see if it satisfied it. And we see that it does.
Okay.
So that makes me feel good that I didn't make a mistake. And then we'll do it for this equation too. I should be able to plug it in both equations and see that it satisfies both. So I'm going to rearrange a little bit. T1, 1/2 plus T2, root 3 over 2 equals mg. Okay? So when I plug these guys in here, that should happen. T1 mg over half. T2 mg. See if this works. This is the point of no return here. mg over 4 plus 3 over 4 mg equals mg. QED. It works. Quod erat demonstratum. It has been shown. That's it?
The whole lesson, man. You got 2 minutes, just in time.
Huh?
It's 26.
Perfect. Well, any questions before I kill this?
I got like 3 minutes.
I got 3 minutes for questions. Any questions? We all good? Okay. Now you have the